Okay, so we have what, till 10 to 12 or something? 12. 15. Okay, I hope that you are still fresh. For me. So this is it. I mean, there is of course lots of work going on in this efficient algorithms, but that is kind of a basic equation that you could use. Maybe just for completeness, there's also something for the derivative of v, right? So first of all, the derivative of v, I mean of vi, the let's call it acceleration of body I, is of course the acceleration of body I minus 1 transformed again. But then there's much more on this. I mean, first of all, of course, there is the same, right? There is this term that we had for the velocity transformation. But then comes this term in here. And if you have a bit of a feeling what it could be, because essentially what it is, it's what you call the Coriolis term, like this, the cross product term that you have when you have a moving frame and you express something in a moving frame, you have this Coriolis term in here. Because when you multiply this, you can take the scalar in, then you have q x times q dot, right? And what is x times q dot? Is the relative velocity. And then we said that this is the kind of a generalized spatial cross product. So essentially, it's the spatial cross product of the relative twist with the body fixed twist of the body. Anyway, so yeah, I'm not going into this. So this is beyond what we're doing. Okay, good. So this is just for completeness. Let's proceed to the what is it then? 6, right? Yeah. Slowly but steadily, we're going to the dynamics. And yeah. So who has done dynamics courses? Some sort of dynamics. 1, 2 dynamics? No? That's going to be challenging. Have you heard about the moment of inertia? What do we do now? Yeah. What do we do? So let's say you have a body, a rigid body. I don't know. Let's say you have one rigid body, right? Like this. And then you are touching a frame, a reference frame, of course. Right? Somewhere in this body. And now so what are dynamic properties of a rigid body? No, dynamic property. I mean, in a sense, inertia properties. Yes. So we have a mass, right? Call it m. What else do we have? So somehow this body has a mass distribution, right? A mass density distribution, right? And that might have, I mean, the body might have, let's say it could be inhomogeneous distribution, but it can also have holes and different geometries and so on. And how do you just, so the mass is a scalar. That's not really something that is describing the whole body, because when you, for example, rotate this pen, for example, then you feel, of course, a resistance, right? And the resistance, if I rotate about this, is different as I rotate about this. It's much bigger, right? And that has to do with the moment of inertia. Now, but even electrical engineering have heard about moment of inertia, I'm pretty sure. I guess, let's say we have a planar body, and you are rotating, for example, about this point, okay, then what they call normally, I don't know what your symbol you use, I don't know, they use J, for example, for the inertia, moment of inertia. Sometimes they use theta. I, this is also something. If this is I don't know what this is. Anyway, yeah. So we use theta simply because, you know, you have seen J as a Jacobian, I as identity matrix, so not to confuse, we use theta. So anyway, for when you are just in the plane, when you're living in flatland, so to say, right, and you rotate about the vertical axis, then there's only one scalar that describes the inertia, which is the whatever the name is. Okay. So in the planar case, you would have which one? You would have two elements. I mean, two properties: the mass and the, let me call it theta then. Okay, fine. But what about 3D? Well, the mass is the mass. I mean, the system has this is a scalar. Okay. What about the, now again, if I rotate about this vertical axis, then I have a theta again, right? So I would have the, whoops, I would have a theta. Okay. But apparently I need more than one, because if I rotate about this one, as I was saying, about this one is different as I rotate about this one. So I need apparently more thetas. But how do I get some sensible theta out of this or things? And then I don't know. I mean, this is another lecture actually. You get something. So let's say rho of R is the mass distribution. Okay, so we have on top of the, or in addition to the mass, or let's say, well, initially when you start, you say you have a certain mass distribution. Let's say rho as a function of the position R. Oops. So how do you get the mass out of the mass density? I don't know. The mass per unit volume, correct. But it might not be homogeneous. So, and this was rho, right? When you want to get rho out of mass. So you said this is mass per unit volume. Okay, what you're saying is, let's say it's like this divided by, I don't know, dV or something. And that is a good idea, because how do you get now the mass? Yeah, essentially it's the opposite operation, right? Like you have rho times dV, and that would be like the mass density or something. Essentially what you have to do, you have to integrate over the volume. And I think we use V for this. V. Anyway, okay. Okay, this is the mass. But what about some sort of inertia moments? Yeah. The mass apparently is independent of any frame, right? I mean, mass is mass. But how do you get an inertia tensor? Or let's say, how do I measure this resistance here? Because the resistance, again, is different if I choose the different point, because now it's more actually. Yeah, that's difficult. So we have to fix a frame. And we say that, yeah, we say there is a frame. So we touch a frame. And relative with respect to this frame, we can actually introduce something that is called, inertia tensor, inertia moments. And it goes like this. As I was saying, there is another lecture to do this. So eventually you get a 6 times 6 matrix. Maybe what is it doing? Maybe just to see what that matrix is doing. Okay, let's stick here. So what is, yeah, maybe we could. What do you know about momentum? Yeah, that's a good idea. Exactly. Yeah, this is a good starting point. Oh. Okay, momentum. Maybe we can do this one too. So the linear momentum, so to say, right? And you say this is like m times v. That's what you said. Okay, how do you call this? Like this. Wonderful. Uh-huh. Now, what about omega? I know, yeah. So can I use omega to get something that has a momentum type of thing? Yeah, I, which is now theta, is equal to, we call it, stop, you call it L. Okay, so you know more than you admit, at least someone. So this is the momentum. I mean, this is the linear momentum, and this is the angular momentum. Now, the linear momentum apparently is independent of the. Is it? Maybe not. Anyway, you have to fix the frame, and relative to this frame, you have the corresponding P and L. Now, what you could do, you could actually plug this into a bigger matrix, and saying, why don't we just yeah, there's a bit of stuff going on here. Look at this one. This one, for example, right? Why don't we call this vector that we get out when we plug in L and P, because this is a vector, right? Again, a 6 vector. Why don't we give it a name and we call it capital P, or pi as they call it in English? Yeah, like this. And then, of course, you have to multiply it with a certain matrix, right? And now the matrix apparently should have some relation to omega and v. And what goes in here is theta, and what goes in here is the mass times the identity matrix, because that's what we need, otherwise it doesn't make sense. So, and if you are in the center of mass, that's an important point. So if you're locating the frame at which you are working at the center of mass, then this is 0. Otherwise it wouldn't. And that's what we get out of here is a momentum screw. Because again, we have a screw property here, right? I mean, in the sense that we have an angular part and a linear part. And again, there is we could, what we did yesterday when we looked at Jacobian and we looked at singularities yesterday, we could actually look into the power, for example, right? So how do you get the power out of when you have, and by the way, this is then, just to make it complete, is m times the twist, okay? And what's the power that we get out of, for example, when we have V and P? Oh, that's what's the kinetic energy? I don't know which one you like. If you have P, for example, how do you get the power capital P? That's a bit strange now. That's what we did yesterday. What is power? Power is force times velocity. Force times velocity. You can also, what? Yeah. Force times velocity. Yeah. Actually, I do this on the spot now because I was not planned to do. What about the kinetic energy? Put it like this. Okay, kinetic energy, let's call it capital T, is a half m v square. Oh, so good start, yeah. In a more kind of abstract way, it's like a half p transposed v, or p times v, whatever you want. So essentially, it's the momentum times the velocity, or more precisely, it's the integral actually of p along dv. But anyway, that's not so. So what about our little exercise here? So what can we do when we say now we have this wrench? I'm sorry, this momentum screw and the twist. Well, I guess it's the same. But before we come there, what about, so this is what? This is the kinetic energy of what? Someone said point mass. Yeah. But we have a rigid body. So there must be something more. Huh? Well, we have the angular part, right? Yeah, we have the angular part that is missing. So essentially, you have a half times. Well, if you stick here, I mean, I would say, first of all, it's omega transpose times theta times omega, right? Which is, of course, the same. I'm not sure what I'm doing now here because it's all mixed up. So this is this. And then, of course, we can now again say, okay, this is, of course, okay, this is what we have to repeat. This is PV. And now comes this omega, no, sorry. Yeah. It comes L transposed omega, exactly. So, yeah. Yeah, and so and all this goes in a compact form in a sense that we can say now for the rigid body, this is of course a half times V transposed MV. So V transposed MV. So this is the momentum. We can also say this is a half times. Yeah, it doesn't make a difference if you this is scalar product, you can transpose it, right? It's the same like V transposed what P. This term, right? Okay, good. I'm not sure what we're going to do with this. Yeah. Now I have to do something in order to get you on track. What can I do? What do you know about the conservation of momentum? What? I don't know what I'm doing here. So what? What did the good old Euler say? There is this momentum conservation law, so to say. What does it say? Remain constant if there's no force acting on it. So momentum, we say probably the linear momentum, right? You would say P dot is 0. That's what you would what you have been saying. If there's no force acting on it. The torque, yeah, okay. That's just the linear momentum. And this applies. Okay, good. What about the angular momentum? I guess it's the same, right? But we have to be precise because now we are working on coordinates because the p vector and the L vector are expressed in a certain frame. Now, what if I have, for example, the p and the L vector expressed in my moving body frame, so in the frame of body I? Is it still true? No, it's not. No, we still have one single body. It's all one body, right? So you said that if you have a single rigid body, this one, if there's no force acting on it, then no gravity, which is the force, then the p is constant. The momentum is constant. That's what you said. And I guess this is also what Euler said. Now, if you're working in coordinates, let's say I have expressed the p. Okay, what is p? P is m times v, right? So let's say I have m times v. Let's call it maybe like this, m and v. So let's say I have the velocity expressed in a body frame, in a moving frame. Is it still correct? No, it's not. So this is what you have to be really careful. This momentum conservation statement is correct. But once you go into coordinate representations, this is only correct if you are representing it all in the inertia frame, correct? Yeah. Of course. Okay, the question, I don't know what we have to somehow get a bit of water, I guess, yeah. Okay, the question was a good question. And what you have been saying is, why is this not correct when you have a moving body vector expressed in a moving body frame? Mm-hmm. Okay. Mm-hmm. Very good. So let's say we have a vector, I don't know, let's say we have a general vector, let's say A, I don't know. So A is expressed in what? The body fixed frame? Inertial frame? Which one do you like? Anyway. Mm-hmm. I don't know. Let's say we have it in the zero frame. I'm not sure how. So let's say we have. So the question is why? And let's say this. You suppose. This was P, right? So when you say P dot is 0, if you express it in a zero frame. So let's first look at what happens actually if you have a frame. Sorry, if you have a vector and you express this vector in different frames, what happens to its time derivative? I think this is a good question. So what we get, we have this R0. Let's say just we have one frame that is 1 and the other one is 0. Okay. So this is the inertia frame and this is moving frame A. Okay. So what can you say about A dot? So A dot is equal to R0 A1 dot, I guess so, plus R1 0 dot A1. Okay, this is not nice because time derivatives of rotation matrices, no good. But what do you know about how can you express a time derivative? That's a very good exercise question of a rotation matrix in terms of some kinematic quantity that you know. We could say, what do we know? No, let alone joint angles. What about the angular velocity? The angular velocity. So because we defined omega, the body fixed version, which means the version expressed in the one frame, as R10 transposed, R10 dot. That was the definition that we used, right? Okay. Which means that we can also say that R dot, I mean R01 dot, is equal to R10 omega tilde 1. So that's it. So you can express the time derivative of the rotation matrix in terms of the angular velocity, the body fixed version, because in a moving frame 1, and the rotation matrix itself. Why is this interesting? Because we can plug it in here. Because what you can find is this is R1 A dot plus, and now comes this R dot, and the R dot is this one, which is R01 omega tilde in the one frame. Times the vector A. Okay. Very nice. Okay, now I can actually transform this equation, I mean the whole equation, because what you get is an equation expressed in space fixed frame. because everything was in a space fixed frame, right? We took the time derivative of A in the space fixed frame. So everything is in a space fixed frame, which you see because of the zeros here. Everything that comes out is in a space fixed frame. What I can do, I can transform this, whatever comes out of here, in the body frame. All right. So I have this A0 dot equal to, okay, if I multiply the whole equation with the transpose of this matrix, right? The transpose of this matrix is the inverse of this matrix, which means this goes away. So then we get A1 dot plus omega tilde A1. Okay. So essentially what I'm saying is the time derivative of this vector expressed the time derivative of that vector was an arbitrary vector expressed in the space fixed frame, transformed to the body fixed frame, right? So the time derivative transformed in the body fixed frame, which is not the same as taking the time derivative of the vector expressed in the body fixed frame. That's important. So this is the vector expressed in the body in the space fixed frame, taking time derivative, and whatever comes out of this transformed in the body fixed frame is related, and now comes it, is related to the time derivative of the same vector when expressed in the moving frame. But there is this additional term. This is the convective term, which is due to the rotation, right? Yeah, this is all I can say. That is also called the Euler formula for taking time derivatives of vectors expressed in moving frames, in moving body frames. Okay. Yes. And in the old version, I mean, not the old version, but in the version that you maybe know, by using the cross product, this is simply omega cross the vector. So, and you find this in many texts, in all good textbooks. The derivative of a vector when expressed in a moving frame is the derivative of the vector plus this convective term, which is omega cross product times the vector. And how can you explain it? I mean, like intuitively, how can you explain this kind of relation? I mean, intuitively, let's say, so you're sitting in the space fixed frame and you're looking at the moving frame. And now in this moving frame, there is a vector. Now this vector is changing itself. Now what you're seeing from sitting in the space fixed frame is the change of the vector, but that is a bit distorted, right? Because the whole thing is moving. And that is this part taken care of. Okay? Okay, now come back to our original question, or let's say statement. We had little p dot is equal to 0 when expressed in a 0 frame. And that's nice. Because now if you plug this in here, in the 0 frame, so I can also say, if I now change this to a moving frame 1, to a moving frame, so I have 1, 0 transposed times the time derivative. This should also be 0. I mean, 0, we can multiply whatever. So 0 remains 0, right? That should be 0. But apparently what you get is something different, because you get p dot in the 1 frame plus omega cross p in the 1 frame. Okay, p dot is 0 because p dot is 0. I mean, if p, I mean, the good thing about 0 is it remains 0, whatever it is. No matter where you express the vector, it remains 0. So this goes, this goes in the bin, okay? But still what we're having is this term, that the p dot vector, so what I'm saying is, your statement, your claim was that this is the same when I express it in a moving frame, which would mean this should be 0. Which is not the case, which is only the case if p is 0. But we didn't say p is 0, we said p is constant. So that's why this is not correct. So you cannot say that P time derivative represented in the moving frame is 0. Even if, I mean P dot, even if the time derivative in the space fixed frame is 0. And that's the important point. And this is what Euler said actually in the beginning.
It is not momentum conservation law is not valid in the moving frame.
The momentum conservation is always valid. This is the thing because it's a physical property. The only thing is how to represent it. And apparently you have to do something else when you represent it in a body fixed frame. And actually, this is what's all about here. You know the Newton-Euler equations. And you know the Newton-Euler equations in a moving body frame? Because this is where it comes, where it gets in. So now I not sure how much we can do without inertia metrics. Yeah. So that's an important first part actually, because let's say you have the one direction. So let's say we have the inertia tensor. I mean, for you guys who don't know the inertia tensor, it was just the one that gives you the angular momentum for a given angular velocity. It's just the counterpart to the linear momentum, right? Instead of mass, you have an inertia tensor. The big difference is the mass is a scalar. They call it also a spherical tensor because no matter in which direction you're moving, it's always the same. This is not the same for the angular momentum because it changes really the direction. You know, this one and that one is different. Anyhow, so if you believe me so far, then we can have this matrix here, and then we have m times the identity matrix. And don't confuse if this was your inertial tensor, then I have to apologize. I'm sorry. Anyway, there's so many symbols out there, right? Yeah. Okay, there's a bit of things. So I was saying this is correct. I mean, the zeros are correct if you're sitting in the center of mass. And only if you're sitting and only if you're sitting in the center of mass, and only if your reference frame is in the center of mass, then this is correct. Otherwise, it's not. Otherwise, you can transform to a different frame, and you know everything. And now you can go home and you can do the rest because you know everything, how it works. Because you know how to transform from one frame to the other, right? But let me do it for you. So let's say that we have another homogeneous transformation matrix, call it S for historical reason, that transforms, by the way, C indicates the center of mass, okay? And there's a matrix that transforms from the center of mass to an arbitrary body fixed frame, right? So we have, I mean, I don't need a picture, I guess. So we have one frame in the center of mass and the other one is somewhere. And anyway, this is a homogeneous matrix. So there's a relative rotation and there's a displacement, and that's it, whatever it is. And then you can get the mass matrix expressed in the B frame by this formula. Maybe we could derive this formula. Okay. We should be, creativity. Creativity means that you use the means that you have to get the job done. And I have no idea if this is working, but we can try. Wait. We can make a patent out of this. Mineral water cleaning. Okay, maybe it was not a good idea. Anyway, we will survive. So, which one? This one. Yeah, okay. How do we do this? So let's maybe have a picture. So we have our frame, which is the center of mass frame. Okay. Okay. And then we have another frame somewhere, maybe here. which is now the body frame I'm interested in. So I would like to express my inertial tensor, all my inertial properties, which you call inertial matrix. This matrix M is a 6 times 6 matrix. Yes, and there is a transformation, that what I said, that goes from C to B. That goes this way, okay? And we call it S. This pattern is not working out. Okay, S, it goes from C to B, okay? Source and target, okay? Always like this. So what can I say? It's all about velocities, right? So I know the velocity in the, I'll put it like this. Again, kinetic energy. And I would like to have the kinetic energy first in the center of mass frame, because this is where I know my inertial matrix. So it is V transposed times mc times V. And now the V should be also indicate this is the center of mass twist. So what else do we know? We know that the velocities are, so if I know this transformation, then I know the velocity of B, at B, so VB, capital B, is equal to at H, so not H, but S, at SBC times VC, okay? And I can use this in here. But when I use it in here, I have to first invert it, right? So VC is the inverse of that thing, the inverse of the adjoint, which is the inverse of SBC. But anyway, let's write it like this. FB, correct. And this I plug in here, okay? So I have done the kinetic energy is the, I hope we have space for this. The kinetic energy is then VB transposed times the adjoint inverse transposed SBC times the adjoint inverse transposed. Now it becomes a bit more, times VB. Okay, times VB, and here is a big dividing line. Okay, and because again, always if you look into transformations of such type of transformations, it's good to look at invariance. I was saying this yesterday. Invariance, because the physics doesn't care about what you're doing. Physics doesn't care about which frame you're using. So the kinetic energy should be the same all the time. That means that there should be a matrix that is called a mass matrix, but now taking care of this body fixed version of the velocity. And that means that you can say there is VB times MB, VB, okay? And MB is then simply, it must be, by definition, what goes in here, which is, okay, everything that goes in there, right? Oh, sorry. It's the adjoint inverse transposed of SBC times MC, and the thing, by the way, this is not transpose, of course, this is just the inverse, right? Because we have just VC, not VC transpose. Inverse SBC. And that's how you get the mass matrix here. So now you have the mass matrix actually in this in an arbitrary frame. And if you do a bit of if you just plug this in, you take this form that we had yesterday for the adjoint, because again, rotation matrix and displacement, and it goes in here. And if you take this, then you get actually explicitly this form of the mass matrix in an arbitrary frame. The mass, of course, remains. Mass is always invariant. Mass is mass. Then you have an inertial tensor, but this one, it is inertial moment matrix. But this inertial moment matrix now is transformed, and it's transformed in this way. So first of all, of course, it's the rotation matrix from left and right, because you have to change the frame. But also there's this additional term here, and this is normally called the parallel axis theorem, which at least you know, and I don't know, you don't know. No, now you know it. It's simply because, as I was saying, if you rotate this thing about, have a bigger one? No, anyway, you can try whatever you want. If you rotate this one about this axis, for example, I can feel something, right? But if I rotate it about this axis, I feel much stronger resistance. And that is actually reflected by the inertial moment about this thing. And this offset is that one. And yeah, and don't get confused. It's not getting less, because when you do the square root of this, it gives you a negative sign, so all becomes positive. So it's not getting like negative mass or something. Okay, good. What else do we need to do? Yeah. Then what can I do? I can. Yeah, then I can. So this kind of operation that we did, so we transformed this inertia matrix, right? That one, from the center of mass to the any arbitrary frame at the body. And that's nice. But I can also, I mean, equally, I can actually transform it to any other frame, right? And for example, I can transform it back to the SpaceX frame, right? And now let's say our body, because we didn't have indices here, our body frame is related to the SpaceX frame by the transformation H0b, right? So H0b goes from the body frame to the SpaceX frame, as always, right? I mean, so far maybe we had an index here I for body I, but we just have one body. Okay, so we have now the body frame, and from the body frame to the SpaceX frame is this H 0b, and because there's only H here, one H here, we get rid of we omit the indices, and so the transformation goes the same. The same argument, you get the same, multiply. So now we go from C to M to B. Now we go from B to the SpaceX frame. It's the same. It's just, you know, a different transformation here. Why do I need this? Because eventually, what Euler said, and Newton kind of repeated it, was that, as you said correctly, I mean, the momentum is invariant. So the momentum doesn't change if the applied forces are zero. Which what you didn't actually explicitly mention, because it was obvious to him to express everything in a SpaceX frame, is that this is true if and only if you have it all expressed in a SpaceX frame. And that's why I like to have, I need to have actually the momentum in a SpaceX frame. And that's what I have, because I have already the mass matrix from this is what we got in the SpaceX frame. And I just have to multiply it with the space fixed twist, which is whatever it is. And then I get momentum. And what he says is the momentum is zero if there are no applied forces. Another statement, a bit more general statement, is the change of momentum is equal to the applied forces and torques. Okay? And that's it, full stop. And now we are there. We have the basic ingredients for dynamics. By the way, what is W? W is called the wrench. So the wrench consists of a moment and a M or T for torque, but torque is not maybe the right word. So the angular part, which is the moment, and the force. Okay. Okay. And now we have this this notion here of SE3 with a star on top of it. Let's not go into this. Essentially, what it is, we talked about SE3, right? SE3 was the space, the vector space of screws. When you have a vector space, there's also the dual space. What is the dual space? The space that is dual to the vector space. Do you know that? It's the space of linear operators. So you can make things very complicated. But you can also make it, you can also try to understand it physically, because linear operators on the space of twists are essentially wrenches. Because if you apply a wrench to a twist, what you get is a scalar, right? Which is what the linear operator does. The scalar in this case is what? Again, it's the power. If you take the scalar product, which is not really a scalar product. But if you take the scalar product of W with V, you get the power, right? And that's why this W is considered to be an element of the dual space. Anyway, sometimes it makes sense to know this, but we don't need it. Okay, now that's the point. Now we get actually almost there, because this statement that the time, the change, put it like this, the change of the momentum is equal to the applied ranges. So that's here, which means that we need to take the time derivative of the spatial momentum. Okay, we know the spatial momentum because it's here, m times v, right? So, product rule, then we have this. So what's the problem here? Maybe the tricky part is this m dot. Because m dot, we have seen that m came from all the way from mc to mb to ms, right? So we would have to take the time derivative of this adjoint here. No, of this adjoint here. Again, we are dealing with rigid bodies, okay? So this is constant. I mean, the inertial properties, if you're sitting on a body, doesn't change. And of course, this doesn't change because also this S transformation is constant. I mean, all the frames that you touch on your body, they all keep the same, pose. The only thing that's changing is age. All right, where are we going now? And this requires the time, as I was saying. So the only thing that we need here is the time derivative of this adjoint of the H matrix. And there we can do the following, because this was what I had at the beginning. There is this time derivative of the adjoint. It looks like this. Just believe it. And now I have to apologize because I didn't change the slides. Again, C is H. Don't get confused. I mean, I don't know. I switched to, and here also. This is somewhere in the transition phase, because for many years I used C and then I switched to H. Sometimes there is a bit of a legacy here. This is still C. Anyway, this is all H, okay? So, I don't know. This is what you have to compute. This is true, believe me. Plug it in here. Anyway, I mean, this is just, doing computations. What you see immediately if you plug this in here, you identify here something that you know. Because this was adjoint of H inverse transposed MB adjoint H inverse. And that's exactly our definition of the space-fixed mass matrix. So essentially this is MS, and the same is here. This is MS. So essentially what you're having is this kind of very nice equation. So the time derivative of the spatial mass matrix is this adjoint transposed minus m times the adjoint Vs. And now what you're doing, you plug this, of course, into what we wanted to do, because this was where we came from. Okay, so now the only thing that is new is this m dot. So the m dot is then this term times v, right? So this times v, and of course this times vs. What can I say? Can I do some simplification here? What did we say about this the little add matrix? We said that this is the kind of a spatial cross product, like a generalized cross product. Just stick with this idea of a cross product. You take a cross product of Vs with Vs itself. If it was just a cross product, what would happen? It's 0. And the same is here. If you go back to the definition of this at, then you see exactly that this term is 0, because the cross product of a vector with itself is 0. And that's why it goes away. And then eventually, that's actually it, because this is P dot, and in the end, this is actually the Newton-Euler equations in the spatial representation. And you can do this even in body fixed version. Okay, maybe stick here for the time being. So this is actually the final version of the Newton-Euler equations. You might not realize that these are Newton-Euler equations because they look totally different, right? But I'm going to show you the detail, I mean, the components of these equations. But what you get is a mass matrix times the acceleration. And now comes again this convective term. And remember what we did before I deleted it when you had your question. What was P time derivative? I mean, the linear momentum time derivative in the moving frame. It was the time derivative of the momentum, right? And let's pretend that mv is our momentum, because this was what we had. Little m, little v was little p. If you take a time, so and then we said the time derivative of this guy represented in this moving frame was it was the mass times its time derivative. And then we said plus omega tilde, which means omega cross product with p, which m times v. Now, if you look a bit careful, what is in here, the first part is exactly this. It's exactly this cross product term. But this kind of combines everything, not only the p, but also the L, the angular momentum. Okay, good. So this, we come back later on this. Yeah, we can do the whole thing in the body fixed representation. Okay, the body fixed representation. Essentially, what I'm doing is, I start from the spatial version here, and I am doing. I'm not sure what I'm doing. Yeah, of course, all the same. I use the spatial velocity. Where is it then? Here, somewhere. The spatial velocity is related to the body fixed velocity by the adjoint, right? So this is at h, which is now c. Anyway, so you go from one to the other with the adjoint matrix. This is what we had yesterday. The body fixed twist and the spatial twist are related by the adjoint of the h matrix. Yeah, and then you plug it in. I mean, you have VB. Why do I do it this way? Yeah, actually, I need the inverse here, right? So Vs is equal to adjoint C or H times Vb. So, and this is what goes in here. Yeah, it goes in here. I don't know. Yeah, okay. I'm sorry. Yeah. So this is where we came from. No, this is, I'm sorry. This is where we, hello? This is where we came from. So ms times v dot, vs dot, and so on. So, and this is ms. So this is what I'm replacing now. So, exactly. So this is where we came from, right? So ms was actually given by mb, left multiplied with this and right multiplied with this. So, and that's fine. So I just plugging in again the ms in terms of mb. Yeah, it says here. Okay, it's all in the slides. Yeah, and then you see immediately, if you identify this term here as the body fixed twist, then you have VB dot, and here you have VB and that's it. Yeah. So, and then of course we need VB dot, because VB dot is of course like, again, take the time derivative, then you have, and so on. Then we take again the time derivative of this at matrix, which we had before, and so on, and so on, and so on. And in the end, you see, what do we see? We get this, the new form actually of the space fixed, the spatial momentum in terms of the body fixed twist, which is kind of a mixture. But now we do the same as we did with your question. We transform the whole thing, whatever we got here, back to the space fixed frame by transforming it with the adjoint of the transpose of the adjoint of the H matrix. And then we have everything expressed, because this gives you W in the body fixed frame, the body fixed range, and then we have exactly what we needed, because then multiply this with this, that goes away, and then we have exactly this term. And what you get here is the Newton-Euler equations in the body fixed representation. Okay, I know it's a bit fast, but you have to go through it. What's important is the result. Okay. Now, if you compare this result with the, do we have this again? No. If you compare that result, try to remember it, with what we get for the space fixed version, you see they are symbolically equivalent, right? So they have the same structure. The only thing is, what is the the reference frame in which it is represented. That's the only difference. All right, so and there we go. So this is, as I was saying, same structure as in the space fixed, but now everything is expressed in the body fixed frame, which means that m is constant, right? Because in the space fixed version, the mass matrix is not invariant. Okay, is it time for? Yeah. Then we should proceed after the dinner.